Morning, everyone. Welcome. It's great to see such an amazing turnout. It's Earth Sciences. There's something in the water with Earth Sciences that they managed to draw so many people. Dave, in particular, thank you so much. We're very happy to have the speaker here, a Waterloo alum. Before I introduce him, I just want to acknowledge that we're in land that belong to the traditional peoples of Neutral Anishinaabe and Haudenosaunee peoples. Our campus is situated on the Haldeman Tract, as you probably know, and I should click to show you the map. The land that was granted to the Six Nations, that includes 6 miles on each side of the Grand River, and our active work towards reconciliation takes place across our campuses through research and learning, teaching, and community building, and centralized within the Indigenous Initiatives Office here on campus at the University of Waterloo. We're very grateful to have Professor Ferré with us here today. As I mentioned, a Waterloo alum. I understood that he was supervised in Earth Sciences by Professor Dave Rudolph. Ty is a distinguished professor in the Department of Hydrology and Atmospheric Sciences at the University of Arizona. Nowadays, I believe he's there already for 25 years or so. He earned a degree in geophysical engineering from the Colorado School of Mines and completed a PhD, as mentioned, in Earth Sciences at the University of Waterloo. And then after a short postdoc position at the University of Victoria, he began at the University of Arizona in 1999. His students investigate topics ranging from direct and geophysical monitoring of vadose zones to groundwater model parameter estimations to increase the role of stakeholders in water resource decision making. Ty was here in 2016 when I just started here as well, because he gave a presentation as part of his 2016 National Groundwater Association Darcy lecture. So let's give a hand of applause to Ty, and I'm happy to welcome you to the floor. Thank you.
All right, make sure I get this guy on. Can everybody hear me okay? And we have a remote. Yeah, excellent, thanks. Okay, so this is the talk today, and I learned several things that I'll try to pass on mostly to students. The first is if you want to get a big audience, you do two things. You have a controversial title, and you have food. So check and check. We're good. And I also wanted to acknowledge that I'm back home. This is great to be here. Thank you, Dave. Thank you, Dean, for having me here and having this opportunity to talk. It's also nice, as my wife pointed out, this is the only place that I still get nervous giving a talk, right? Coming to Waterloo. So, and it really helped that Dave arranged to have this in the exact same room where I defended my PhD. So I could come right back to feeling that way. So today, here's our controversial title. It's good to get people off guard a little bit and then to put them at ease. So I'll put you at ease right away. I think hydrogeology is super important. So I'm not going to, if you came for a talk that was going to tell you why you don't have to worry about groundwater, this is the wrong talk. On the other hand, I still don't think that we're really doing it as well as we could. And we're not doing it as well as we could to serve sort of the missions that I think are central to groundwater. So I'm going to start with some basic propositions, mostly to make sure that you know where I'm coming from, see if we're on the same page about what hydrogeology is. The first is that it is an applied science. We increasingly have a lot of cutting-edge work that's happening in hydrogeology. I think that's fantastic, it's laudable, it's part of our field, but ultimately I feel like the beating heart of hydrogeology is what we do for society and how we apply our science. And in particular, I would say that the role that we play is we're trying to help people to make better decisions about water. So we play a role in that decision-making process. We rarely make the decisions, but hopefully we make the decisions better. And the nature of hydrogeology is that all of these decisions are being made under considerable uncertainty. So we have very little data. Those data often tend to be fairly noisy. We have very complex systems that we're dealing with. So our role is to help people to see through the uncertainty and see what uncertainty remains so that they can use that as part of their decision-making process. So I am a simple person, so I like to think in very simple examples. Many of you have worked in much more complicated cases, and so I'll invite you to map any case you want to onto this. But to drive this conversation, I want us to think about basically the simplest hydrogeology problem you can imagine. So we have some factory or something that's going to release a pulse of contaminant, And conveniently, it releases it right into a homogeneous aquifer that flows purely horizontally. And we have set up our monitoring well right along the axis of that plume. And our municipal well, our point of compliance of other type, is down gradient. So life is very simple. And in fact, it's so simple, we understand the processes. We know perhaps which processes may occur. We know something about the range of parameters that might apply for this site. So we can already make some kinds of predictions about what might happen at this site, even without any measurements. So we can limit what we might see at the monitoring well, so what we might measure, which helps us to design and understand what kind of measurements to take. And we have some range of possible outcomes down gradient. So the best case scenario is all of these possible outcomes are below some kind of limit, and we can say there's no problem at all, right? The second best is every single one of those turns out to be a problem, so people can make a very simple decision. Most often we have something that looks more like this. Before we go out and make measurements, the science alone, our knowledge alone, does not allow us to narrow down the possible outcomes enough so that we can lead somebody to make a clear decision. So what do? We add data. And here I want to take a little bit of a side. I think now every talk is required to include AI at least once, so I'll include it in this part. I want to talk about what models are and what data are. So my thought about this is that a model tells us, or it describes the realm of possible outcomes, and then data allows us to choose or identify which of those outcomes is most likely to apply to a specific situation. So another way to say that is models are a way that we map what we can measure onto what might happen. So it's simply making that map and allowing us then to take data that we have now that's available and use it to make some decision about something that hasn't happened yet. So with this in mind, we often present our science to people outside of the discipline and say it's relatively simple. We collect data, we match a model, we can then use that model to make predictions. And if we're not pushed too hard on it, we'll sort of assume that those data are enough to really constrain our model, and that allows us to make good predictions that people can use reliably to make decisions. If we're pushed at all, or if people happen to see our data, we recognize that our data do have errors in them, but then we fall back on this idea that, well, sure, there are these small random errors in our data, but our models are strong enough and meaningful enough that we can see through these errors, come to what's really the underlying truth of this situation beyond those random errors, and still make reliable predictions. And then for very knowledgeable people, they'll say, but you don't have very many measurements to rely on. And we usually don't say anything. We'll say, okay, that's fine. All right, so this is where we stand. And then what we do with this is we pass this on to a stakeholder, and that stakeholder may produce their own limit on some kind of prediction from the model, or there may be some legislative limit or regulatory limit. And they use that to say, is there going to be a problem or isn't there going to be a problem? So in this case, we have these measurements in the blue at some point, and we're predicting what's going to happen later at some greater distance. And we're having to decide whether or not, for instance, we need to enact some kind of treatment. So is this something that we have to care about? And that's what we ask the stakeholders to do. So we can go a step further than that. Since we have this quantitative tool, we can use it to then design what our treatment might be. And we'll say, well, maybe we have a very simple treatment in mind. It's something that has only 2 design parameters. We have to decide when to start treating and how large our treatment facility might be, what its capacity might be. And then after that point that we start treating, we're going to reduce the concentration by some certain amount. And we can also include that in our model. And we can say, what does our model tell us about what's likely to happen based on our understanding, our data, and our design? But of course, this isn't an optimal design. In this case, we could look at this and say, well, the start time, clearly we're planning on starting this too early. Why would we do that? Why start treating when we don't have to? And depending upon your take on this, maybe we're treating this too much. We're not close enough to that limit, or maybe we're not treating it enough. We shouldn't let any contaminant go by. So we have this question of optimization of the design. Of course, if you ask what is optimal, then the answer that you'll get depends on who you ask. So an optimal design has to have some criterion on which it's optimized, and then we're choosing these parameters, these design parameters, to meet that optimization. So in this case, for instance, if we were to ask the factory owner what is an optimal design, and we say you have this range of start times and this range of treatment capacities, they're always going to choose to start as late as possible and treat as little as possible, right? And that's not because they're evil, it's because that's what their optimization says. We want to spend the smallest amount that we are required to spend. And we can look at any one of these designs, and the advantage for something like a factory is they can translate what this design would be into an actual cost of treatment. There might be some uncertainty with it, but at least they can really turn this into an economic factor. And so we can look at multiple different designs and we can plot what their costs would be. And on the bottom right, there you see a little star peeking out. That is what their optimal might be. Now, if you asked the town, you might get, and sorry, I should say that for the factory, this is relatively simple because you can monetize, but for other stakeholders, you may not be able to. If you have the town down gradient, they may also be able to turn their outcomes into monetary equivalents. So maybe I have to treat water, maybe I have to replace my water. Any one of these outcomes that we predict after treatment will have a certain cost for the town. Their cost surface looks different because their priorities are different. And then also they have the significant difference that there are multiple equally optimal designs for them. And the only thing that they have in common is that they're not the same one as the factory, right? So for the town, any way that you completely clean up the plume is fine by them. If you want to spend more money, if you want to start earlier or later, as long as you clean up the plume, it is identical to them. It's a little bit more difficult if we think of something like the environment. So maybe somebody's representing the environment, somebody's representing cultural use of water. It may be not only difficult, but actually really inappropriate to try to turn this into a monetary value. So essentially what we're saying is, by turning this into an equivalent monetary value, is how much would you pay to give up the environment? How much would you pay to give up this cultural value that you have? So one approach that people take is to use a term that's called utility. And utility is a nice way to make this very vanilla. We're essentially saying we have multiple outcomes, and we just want you to relate this to how satisfied you might be or how acceptable an outcome might be. And this can range everywhere from 0, meaning that it is so bad that if it got any worse, I'd still be just as unhappy. I'm as unhappy as I can be, all the way up to 1, to say, if it got any better, I wouldn't care. I'm already so happy. And then we can map, not easily, but we can map the satisfaction or utility against some prediction or set of predictions from the model. And this is really the key to how people use models, whether they know it or not. We are giving them some prediction, and they're mapping that in their minds to how happy or unhappy will I be if that happens. So it's worth trying to find this utility, and of course we often then take this utility and map it onto cost. And we do that by valuation. So we say if you're 50% or your utility is 0.5, it's worth $1 million, whatever that might be, whatever number. So why do we do this? Well, first of all, it allows us to relate everything on the same basis. So we can say for the environment, they have, again, a different cost function for different designs. They, again, have multiple optimal designs that they might choose. But we have to recognize that we have done this perhaps inappropriate thing. And we also recognize that we're left with this case where we have 3 different stakeholders, and all we've done is tell them, hey, you all disagree with each other. So we haven't really helped all that much yet. So what's the obvious way to go forward from here? What do you think? Add them up, right? That's why we evaluate in the first place, right? Is so that they're all the same basis, and we can say, well, if everybody's talking in dollars, whether it's Canadian or American, then we can just add them up and we can find the minimum, right? And we can do our optimization based on our model, based on our data, and we can say, this is what you should do, right? Of course, we have a lot of assumptions built into that. And our role, again, is if we measured something different, then the cost functions for every one of these would have been different, and so we would end up with a different optimal treatment. But it's a way that we're trying to map our skill, our insights, into decisions that people may have to make. There is an old adage, of course, and it applies here. And if we are honest with ourselves and we look at the way we're doing this, then we recognize that it's clearly too simple. We're making some broad assumptions that may have some real impacts on people. So the question again, you don't have to say it out loud if you don't want to, but what are the assumptions that we're making? Where are the pitfalls for this too simple approach? So I'm going to suggest that there are 3. You may think of others. The first, of course, is that our model is too simple. Our model is wrong, or somehow everything that we're trying to make our advice based upon is based on a fallacy, or some kind of fallacy. The second, of course, is that our data are sparse and our data are uncertain. So even if our model is really good, we don't end up with a single prediction. We end up with a set of multiple predictions that are each at least defensible. And then the last is that this stakeholder valuation, turning their utility into dollars and cents, is always difficult, and sometimes it's highly inappropriate, in my opinion. So that brings us back to the start. I'm sure that we are still making a difference. We are pushing things along, but I think that with some relatively easy fixes, we could actually do considerably better. And in particular, we could do considerably better considering that every decision that we are faced with, we're trying to support decisions under uncertainty. Okay, so let's go back to our simple example and simply add some uncertainty. So we end up with something that looks like this. So now we have the same data, the same limit, everything is the same, but we're just acknowledging that in this case, maybe we could fit 4 different models to these data to differing degrees of acceptability or differing degrees of agreement with the data. So we end up with these 4 models that look relatively similar in regard to the data that we have, but they make meaningfully different predictions. So some of them say there's going to be a problem, some of them say there's not. So we end up with this case where we have now said to stakeholders, we've done all of our work, it's uncertain, you decide. So we haven't really helped them out all that much, right? So how can we go forward? How can they decide? What can we tell them to do? Well, the simplest thing to do is to look at these and say, well, one of these models fits better than the others, so use that one, right? And if we do that, it takes us all the way back to the beginning. This is the underlying problem of our limitation of our simple design, is we're saying we know that there are lots of models that might fit the data. One fits maybe marginally better, use that one, right? Another approach that we can take is to somehow say we're going to give you one prediction, but we're going to try to consider all of these models. So we're going to use something like a likelihood-weighted prediction. So we're going to look at how well each model fits the data. The better it fits the data, the more heavily we'll weight it in our prediction, in our average prediction, and we'll come up with something like a wisdom of the crowd kind of prediction, where we're saying that we are honoring these other models, but we're still trying to come to a single prediction that you can use. All right. This is where I'm going to take a little bit of a diversion here for a moment. And for those of you who are already experts in Bayesian knowledge, you can check your phones or do something else. It'll just be a couple of minutes. But for those of you who aren't, it's really important to introduce the first hero of our story, Thomas Bayes, and how he relates here. So we started out here where we had what we call an ensemble of equally plausible models. So these are all based on what we know and what we think about the system, but we have no data, right, just to put us in the right context. And so without any data, we have to consider that any one of these is plausible, and we can even say equally plausible. Then what we're going to do is we're going to take these and we're going to relate them to some kind of output or series or collection of outputs and use those as the basis for people's decisions. So I'm going to take a really simple one. I'm just going to say the maximum concentration is all that we care about. And rather than look at hundreds of models, I'm just going to consider 20 of them. And the first step is that we can say, of these 20 models that we have, they make a range of predictions of interest, and we're just going to sort them, right? We're going to say this is the range of predictions that we have, from the best to the worst, for instance. And then we say that someone, whether it's a stakeholder or the regulators, puts a limit on this. And right away, without having any data, we can look at this and say, well, out of our 20 models, 3 of them exceed the limit, and so there's a 15% probability of exceedance, right? So we've already helped somewhat. And the question is then, how do we improve things by collecting data? Why do we do this painful thing called data collection? And really, to understand this in a Bayesian sense, we have to remember that what a model is a way to map data that we can collect onto predictions that we have to make about the future. So we can think of this in a really simple sense, saying we have one thing that we observe and one thing that we care about, and we're just going to make a correlation between the two. And the better that correlation, really we're saying the better our model is at making a map between what we collect and what we want to predict. And then we imagine that we go out to the field and we make one measurement, right? So again, keeping things simple. We measure 5 plus or minus 1, whatever those units might be. I'm not a chemist. Okay, at this point we're saying we have this one measurement. We're going to take a very simple approach to this. We're going to say anything that matches that measurement is a valid model, and anything that doesn't, we're going to throw it away, right? So we're going to make it really, really simple for ourselves. And now we end up with only 9 models that are valid or plausible models. And we can say of those models, 3 of them exceed. So adding these data has changed our interpretation of the risk from 33% chance to 15% chance. Did I do that the other way? 15 to 33. So the data have informed us, and they have helped us to make a better projection and a better estimation of the risk. All right, let's turn this into a little bit of probability speak. So what we're doing is we're saying, we're going to start out by saying, what is the probability that any of our models is going to match our observations? So the P of O probability that we're going to match an observation. In this case, 9 of our 20 models do. And the next thing we're going to do is to say, of those models that match our observations, what is the chance that one of those is going to lead to exceedance? So in this case, we end up with 3 over 9. And what this allows us to form is this probability that any model is going to do both. It's both going to match our observations and lead to exceedance, right? Right now, it's not that useful, but it's a step along the way. So we have this way to come up with the probability that something's going to be in that small box from our entire set of models that we started with. Now, we can, of course, do this the other way. We can start with saying, what's the probability that any one of the models is going to exceed? And then given that a model exceeds, what's the probability that it would match the data? We end up with this same expression of the probability of both. It's convenient that it turns out to be the same number. Otherwise, I did something wrong. And this is really where the magic happens, because we have 2 statements that give us the same thing, this probability that something's going to match both. And then we can simply take this and set those 2 equal to each other, do a little bit of recombination, and we end up with this exceedingly useful thing, which is saying, if I have my models, my collection of models, and I have my data, now what is the chance or the probability that we're going to have exceedance given the observations that I have, right? Okay. This, for those of you who have been scanning your phones for the last 5 or so minutes, this is just Bayes' law. And it comes out to be exactly the same thing. It's 33%, as we said before. So Bayes' law, just to pull it apart a little bit, it's often stated in words as the posterior probability is the prior probability multiplied by the Bayes factor. And a lot that's buried in this, but simply stated, the prior probability is what we thought was going to happen before we confronted our expectations with data. So when we went into this before we added data, what did we think the probability of some outcome might be? Posterior is what do we think after we've considered the data and updated our probabilities. And this Bayes factor is an extremely important and very much overlooked thing, which states that different data have different abilities to change our mind. And so we're really ideally looking for data that have the ability to change our mind from our prior, right? So we usually don't do that. We just collect data and then hope for the best. But it still has a Bayes factor. Okay. Good. So as scientists, how do we use Bayes? Well, typically the way we use Bayes is we stand on a pedestal somewhere and we say, we are objective. We have no biases. We try to make sure that we are only looking at the data and what the data and the models tell us. And what that means is that we have no prior expectation of an outcome. So another way to say this mathematically is we have a uniform prior. Every possible outcome is equally likely. And you'll perhaps recognize that I used exactly those terms when I said we have an ensemble of models that have to be considered to be equally likely. And nobody raised their hand and said, well, that's ridiculous, right? Because that's what we do, right? We like this. And what it allows us to say is that we're essentially letting the data speak for themselves. We're not injecting any bias into the situation. That sounds great, right? I mean, it's a room full of scientists, right? We all agree with this. The problem is that this is not at all how stakeholders see it, and it's not at all useful for stakeholders. So the prior is the place that the stakeholders get to state what they care about and how much they care about it. It's the place that they get to state their context for the problem. And so we have this fundamental problem where we have a different interpretation of what the prior should be than the stakeholders. And often we just blindly sort of push them into using our context. And another way to say this is And I started out by saying stakeholders will change their mind if they're confronted with enough data, convincing data. And then I realized in reality they may change their mind, they might not. But at least there's some hope that if they tell us what they're concerned about and we present some kind of analysis that directly confronts their concerns, that they are at least capable of changing their minds. All right, that was a divergence, so we're back. Here's where we were. We're at this stage where we had our combined cost function, we're optimizing, and we're finding out just how we should design something, and we had these three problems, that the data are noisy and sparse, the model is, the stakeholder evaluation is difficult, and the model might be wrong. So let's look at each of those. So this problem with the noisy, sparse data, again, it comes down to the fact that because of the noisiness and the sparseness of our data, there are multiple models that can be defended. There are multiple models that may be correct. So this leads us to having these multiple models, and our approach again is to say, let's use a likelihood-weighted average of the models based on how well they fit the data. From a Bayesian perspective, really what we're saying is that you can only use the data to assess the likeliness of these models. You are not allowed to have a different prior if you use likelihood-weighted averaging. And if we go through just a little bit of math, this is only true if we have a uniform prior. So the likelihood weighting of models is a direct consequence of assuming a uniform prior, right? Okay. So this doesn't really fit with what stakeholders do. So is there a fix? I think there's a relatively easy fix, in fact, is that we can allow the stakeholders to express their belief as the prior. And then we go forward and do everything that we've done before. We just are now confronting their prior probability with the data. And those data have to meet a higher bar because they maybe are more skeptical, right? So essentially what we're doing, and one example of it is, we just look at this set of models and we say, well, 3 of these models exceed the expectation. In this case, the number doesn't matter, but the stakeholder may say, I think there's a 75% or a 90% chance of exceedance. I think that there's a really high chance that there's going to be contamination here. You have to convince me otherwise. So we take this 90%, we distribute it among the models the different ways that there might be exceedance, and then we take the remaining 25% and we give it to the models that don't have exceedance. So now we have a prior and we continue to confront it with data and we're continuing to update, and it just might take a little bit longer to get to the same conclusion, but at least we have directly considered and included the stakeholders' concerns. So the downside of this is often people will say, but this bias, you're introducing bias in your scientific analysis. And we've done lots and lots of studies with this now, and we've shown that that really makes very little difference because we're putting these things forward as possibilities, but we're still maintaining that they have to be tested against the data. And essentially what it does is it allows us to bring the stakeholders in and say, we are directly considering what you are concerned about, and we're trying to improve it or trying to test it. Next problem is stakeholder evaluation. Might be difficult, might be impossible, might be inappropriate. We get to the second hero of our story, a guy with the best name maybe ever, Vilfredo Pareto. And he is one of 2 ways that he's going to enter our story is he says, if you do this valuation so that you can make an easy single decision, maybe the problem was that you shouldn't have made an easy single decision in the first place. So we're at this point where we have multiple possibilities and we ask, how can we move forward if we don't want to tie ourselves to valuation? And so Pareto optimization is the answer to this, in my opinion. So just pulling apart one example here. Let's say we're looking at a trade-off between what the factory wants and what the town wants. And we have these 2 cost surfaces. And what I've done is I've traced out a line on the town's cost where any one of those ends up with exactly the same cost for the town. So the town does not care which one of those you choose in terms of the outcome. But if we follow that same trace along the factory, we find that the factory does have a preference. There is a minimum cost to the factory along that trajectory. And that shows on the right here, if we go along this red line, all of which have the same cost for the town, we have multiple options that have different costs for the factory. So for that specific case, we can find an optimal. That's one of many optimals. So this set of red dots is our Pareto optimal space. It is the set of optimal trade-offs between the town and the factory. We're not saying which one is the best, we're just saying you should really only consider these because any other design is less optimal. We can do the same thing between the town and the environment, or the factory and the environment. It'll have a different shape because they have different cost functions. We could still come down to the same set, or different set of Pareto optimal designs. And one nice thing about Pareto optimality, it's easy to see in 2D, but there's no limit on how many stakeholders you can include. You could have 1,000 stakeholders and look for Pareto optimal designs among all of them. And in this case, we have 3, and so we can show it in terms of 2D space between the environment and the town, but you'll see that we have this collection of red points, all of which represent an ideal or an optimal, one optimal trade-off among those 3 stakeholders. So what we've done is we've reduced from an infinite number of possible designs to a reduced number of locally optimal designs. We still haven't left them with an answer, of course. So what do they do from there? Well, the first thing that I would say is when we have a limited number of designs and we can define the utility, and this can work in both utility and cost space, forgot to mention that, and one stakeholder can have utility and the other can have cost. There's no limit on that. We're not combining them in that way. So in this case, we can say the difference between this design and this design is you will lose this much in utility and you will gain this much in cost. So we can start talking about whether or not they're willing to make compromises, specific compromises on a set of optimal designs. Now, we can, of course, decide that, well, what we want to do is find the maximum for everyone. So we want to sum up all the costs or sum the utilities in some way. And that gets us exactly right back to what we usually do. And the valuation is just one of the designs on the Pareto optimal front. It has to be, right? Because it is an optimal design. But imagine that we don't have a factory. We don't have some evil player in there. We have 3 very deserving stakeholders, each of whom has a different use for water. Maybe the best thing to do is not to come up with the lowest total cost, which might leave one of those stakeholders really unhappy. Maybe we want to find the lowest difference in costs. Maybe we want to have everybody gain and suffer about the same. That's just another limitation that we can put on this. And again, from the Pareto front, we can find any number of solutions. We can add any additional constraint to come up with a single solution. But that single solution is not imposed by us for simplicity. It's actually through conversation with figuring out how they want to make a compromise. Then the last thing. Model might be too simple or it might be just wrong. In fact, I mean, there's a statement that they're always wrong, right? But just how wrong are they? How useful are they? So this, again, we come back to this role of the models and the data. And what I stated earlier on is my take on this is that the models tell us the range of plausible outcomes. It's the range of outcomes that we're considering, or the range of descriptions of a system that we're considering. And then the data help us to determine which of those is the most likely. So in this case, the important thing is that we decide what things we're considering. And this is where Pareto comes in again. He noticed, which sounds incredibly quaint, I know when I say it, that 20% of the population owns 80% of the wealth. It was a while ago, right? It's a little different now. So nonetheless, that we have this very small number of outcomes that have an outsized impact. And really, my claim is simply that our job, our main job as hydrologists, is to be able to identify those plausible outcomes that would have a big impact if they were true. And again, what we're really doing is not trying to find the simplest model that describes the system, which we often tell ourselves is our goal. We're really trying to find the range of models that are scientifically plausible, supported by the data that we have, and collect all of those together and then move forward with looking at data and seeing whether or not we can discount some or not. So essentially what I'm saying is that the job of the hydrogeologist is to look for these vital few consequential models to include in our ensemble so that we are making sure that we are taking care of these possible outliers. And this has gone by a number of different names. The one that I like the most is this hydrologic surprise. I think Bredehoff came up with that. We're surprised by, we didn't think there might be a fault there. Why not? Why didn't we just put that in a model and see whether it was supported by the data and if it was consequential? So that's where we come. So I started out by saying that I think hydrogeology is really important. I still do. I do think that we have some relatively, I think, simple fixes that we can impose in the way that we practice hydrogeology to make it more effective and more useful for stakeholders. It comes down to these 3 recommendations. The first is, I'm a strong believer in Bayesian analysis, but Bayesian analysis is only as good as the models that you put in and what you allow people to include in their Bayesian analysis. So I think it is defensible and, in fact, the right thing to do to allow stakeholders to include their bias in the prior and then insist that that prior be tested against data. The second is to use Pareto optimization. So often when we do optimization, we unintentionally, I would say, make assumptions about what is optimal, and then we go forward and do a lot of work to come up with these optimal solutions. And I think that if we take a step back and look at the range of optimal solutions, possible optimal trade-offs, that we're actually doing much more of a service for people who are trying to make negotiations or trying to make these collective decisions. And then the last of these is, of course, that I really think that where hydrologic insight comes in, where our expertise comes in, is imagining these things that might be. So we often think of ourselves as going out to collect data to describe or define what's in the field. And I think it's much more powerful and much more useful if we use our hydrologic insight and the range of data that we have to say what might be there, and then test whether or not that's what's there. So rather than making, again, a decision early on about a model and then doing some small variations around that model, let's try to be much more inclusive of the models that we put into our ensemble. So I'm not sure if that answered the question that I put up there to begin with, but I think that that is the use of hydrogeology. The use is that we help people to make better decisions under uncertainty, and I think that the way that we can do that is honoring their concerns and improving our analysis so that we're actually presenting them with richer data to make those decisions. All right, that's it. Thank you so much.
Thank you very much, Tai. So we have time for questions.
Made it on time.
Does anyone want to start off?
Steve
Just give me a
Sikorsky,
second.
how you doing?
Good to see you.
Good to see you.
I'm curious about what the language or the communication is like when you start using Bayesian and Pareto and things like that with stakeholders, with the public, and so on. You're speaking to a room of scientists and engineers here
Yeah.
who we can, you know,
We can get it.
we can kind of get it.
Yeah, exactly. Yeah, so it's a great question. So one of the things that I do is I act as what I call a hydrologic intermediary. So right now I'm working on a project in Arizona where there's a mine that wants to extract water for removing ore, and there's a nearby community that has concerns about what's going to happen. And so my role there is to try to make sure that the community's concerns are communicated to the mine so that they build their model that will answer their questions, and that the mine, the assumptions and the way that they do the modeling can be translated back to the community. So right in that space that you're talking about. And I think what's important is you never say Bayesian and you never say Pareto, right? So really what we're saying is, tell me what you're concerned about. Let me make sure that they're building a model that will test that possible outcome. And if they do that, will it help you to change your mind, right? And so I think that in this Bayesian, or both of these really, we're coming to that in using sort of common language. But in this room, we understand what we're doing. Does that sort of answer your question?
Yeah. So who's funding you then? Are you just as an academic, or are you?
Yeah,
How did you get into that?
This is a great question. And this case worked really well. So the way it worked was the mine gave money to the Citizens Council to use as they saw fit, and then the Citizens Council hired me to act as the intermediary. It so happened that the main hydrologist in the mine was also my PhD student, so it made it a little easier, but nonetheless. And there's a continuing struggle of trust there. Absolutely, no question whatsoever. Yeah, good. Yeah, thanks.
Anyone
Yeah.
else?
Speaking of, I guess, trust, who's sorry, I'm Christian Durkin from WaterTalk Hydrogeology,
Hey, Chris.
and one of your former students too.
Yeah.
Whose prior are you using in that situation then? Because you could use the towns or you could use the mines, and they're probably going to be different.
Yeah. So in that sense of coming up with, we're not at a stage where we're coming up with a design. So in a sense, we don't need to have that specific prior, but we can think of using that prior in saying what we're going to start out with is the assumption that there's a problem, right? And so that really changes the way that we build the ensemble. And then, in fact, if you build your what we found is if you build your ensemble to include these models, what we call models of concern, you almost don't have to worry about the prior so much. Because if I use a uniform prior, but I've made sure to seed the ensemble with models of concern, I've essentially included their prior in that way too. Yeah, but it's a great question. Yeah, good, thanks. Good to see you again.
Hi.
Hey.
You mentioned once you do the modeling, there can be a step where you're discussing with both parties which objective options might be chosen on other bases. I'm wondering if you've done mapping of specific values of what qualities, qualitative or quantitative factors are important to the stakeholders. Is there a mapping of what goes into valuing those options?
Yeah, it's a good question, and it would probably be very hard to sort of really get those numbers from stakeholders about what their value is in a sense. But what you can do is things like, if the mine, for instance, they were thinking about 3 different ways to deal with pumped water, because in this case, really the primary concern up front is that the mine's going to be releasing too much water into the stream and they're going to get flooding. So it's really about thinking with these different designs that they're proposing and saying what are the possible risks with those designs and how comfortable are you as stakeholders with each of these levels of risk. And then the mine on its own can be saying like, well, one costs 25 times as much as the other, so if you're just a little bit more concerned, I'm okay with that. Yeah.
Would you have as a project exit, a mapping of some values that you weren't able to consider? Is that something that you map out?
It's a great question. I'm not really sure. So in a sense, like if somebody said, I'm concerned about the color of the water, but I don't know how concerned I am, right? This, in my mind, this is the biggest challenge that we have is, and I've been working with this citizens group for about 1.5 years, and I spent a year of it just trying to get them to say what they were concerned about and how concerned, right? And then, you'll get a year into it and they're like, oh, but what about this? Like, I just spent all this time begging you for what are you concerned about? So I think we are always also going to have these things that come up later or things that come up and they're like, well, I'm kind of concerned about that, but I don't know how. Yeah, it's a good question. Yeah. Oh, sorry. I'm crinkling all over the place. I don't know why, but.
Am I correct in assuming that all of the priors between like the environment, the factory that you gave in the example, they're going to be equally weighted in a sense?
So it's a really good question. I think that what you can, the easiest way to think about that is that each stakeholder will essentially have a different prior, therefore a different posterior. And what that means is that the data that you collect may start to convince some stakeholders before it convinces others. And I think that's a real description of, if we want to go into stereotypes, the town might be pretty happy pretty soon, and the environmental folks might be like, no, I need more convincing, right? And that's simply a statement of their prior, which goes to how convincing do those data have to be in the context of models to get me over the hump, to change my posterior. Yeah, so each would be separate.
Is there ever a situation that you have been in personally where something like a factory or other stakeholders have said, no, my concerns are more important than the environment or the towns?
Every one of them.
Yeah.
Okay. And the way that it usually happens, they're savvy now, so they don't come out and just say, I don't care what you think. What they say is, let's put a dollar value on that, right? And they say, let's put a dollar value on the value to the town of their water supply. And then you look at this mine that has a $200 million budget, and they're like, yeah, we can pay that. That's not a problem, right? For us, it's not a problem. But it's just making this basis. If you try to move away from things and empower people to say, like, your concerns matter, and where you fall in this shouldn't be translated to large deep pockets of another company, something like that. Anyway, I'm rambling. If that answers your question.
There's another question. Yeah, I'm right here. Grace Ferguson from Stantec Consulting. So having been in the consulting field for a number of years, it's just a comment more than anything, just that you don't have to be numerical modeling when you're talking about models here.
Yeah.
We often don't have the funding to support a large numerical modeling exercise, but when we have situations like this, consultants find themselves in that role of intermediary, trying to interpret the hydrogeology for multiple stakeholders.
Yeah.
And it's a great way to look at it, to find what's of concern to them, and also considering more than just one model, because you do come at it with a bias, whether we like to admit it or not.
Or not, yeah.
We always come at that problem with, okay, this is what I'm thinking is going on, and you might be influenced by who your client is, for example.
Right.
But opening it up to consider those other things that might be of concern to stakeholders is really, really valuable insights.
Good.
Thank you.
Yeah, and what you've seen before colors what you expect, and all sorts of things that we don't recognize, right? I mean, there are whole fields of study about that now, right? And the only thing that I'll say is I agree entirely that numerical models or any kind of quantitative model, let's say, is not necessary. The difficulty is that for this approach to work, we have to be able to allow people to say this is my concern and then guide them towards testing against data. And so that can be a problem when you have just a conceptual model. Then they have to just rely on you to say, like, I know you're worried about that, but that's not going to happen. Yeah, don't worry.
We have another question.
So hi, my name is Suren. I'm from Aqua and Water, which is a clean tech startup.
Yeah.
So I actually have two questions regarding the future of this modeling and basically the design that you were explaining. How do you think the technology that might be coming in the future might affect this modeling, like atmospheric water generation or something similar to that? And the other question is, how do you think the new tools available to basically scientists, like machine learning or AI techniques, might be affecting these modeling methods and might be changing some part of it, or maybe even making it redundant somehow?
I'm gonna preface this by saying I know about 20 people in this room that know more about modeling than I do. So I'm not even gonna try to really dive into it, but I'll tell you my opinion about it, okay? And I think that the machine learning to me is not fundamentally different, if I'm honest. We're taking in different amounts of data. We can use data that otherwise, for instance, we may need to have 3 coupled models in order to use this data, whereas allowing this to be a kind of correlation machine allows us to see the value in those data. So I think fundamentally the approaches that people will take, and models are getting much more efficient and they're much more thoughtful. And also there are a lot of inversion techniques that are coming out now that allow us to identify some of these models of concern and allow us to tell more about uncertainty. So modeling continues to advance. I honestly don't think that modeling capability is our limit right now. If I'm honest, I think the bigger concern, or the bigger limit that I hear is consultants will say, that's great, my client won't pay for it. They won't pay to build 3 models, they'll barely pay to build 1 model, right? So part of it is getting out, and folks like you, and saying, like, this is why we need to think about things more carefully or more creatively. You were talking about different treatment possibilities?
Different treatment or even different water resources that might be available in the future, which are not really discussed yet.
Yeah, so I mean, just in this framework, I think what I would say is that that's one of the solutions that we have to consider, right? So if we're thinking about our solution space, it may be, you can clean up this water, you can just leave it polluted and use cloud water, whatever the new thing might be, right? And so I think that will come into those spaces. It will also come into those cost functions. So if we had some, brand new technology that could clean up groundwater at very low cost, it would totally change the cost function for that factory, and it would probably really shift what the optimal design would be, or set of optimal designs would be. Yeah, good, thanks.
Anyone else? We still have some time.
All right. This side of the room is really underrepresented. I don't know. It's all the faculty sat over here, and they.
Still on this side of the room.
All right, good.
Just about the idea of this technology. So I'll relate to myself personally. I'm a postdoc now. My father has, I've done all my education in hydrology, but my father is not a scientist, and he's like, why can't we we live by the ocean, he's like, why can't we just treat the ocean water? Right. And I don't know how many other people kind of come up with that topic from lay people, but it makes me think about this idea of cost and this idea of the prior is do you encounter situations where people assume that a technology could exist at a certain cost to solve the problem, and if you were saying treat ocean water, the technology exists, but it's very costly even under current technology. Do you find that bias exists, that people think that there is a easier solution for a given cost than there really is?
Yeah, and I think, this is really relevant for us. So in Arizona, the government opened up this thing to say, surprise, surprise, we live in a desert. Having more water would be great, right? Fantastic. So if you can come up with a way to do it, we'll give you $100 million, right? So all of the academics, we all had our hair in knots and we were thinking about it. And then this Israeli firm came up out of nowhere, and they said, oh, we have the solution. It's easy. We run a pipeline from the Gulf of Mexico, we desalinate the water, and we bring it up to Arizona, right? So great, that's fantastic. And I think this is often what happens is we're missing a stakeholder, right? And that stakeholder in this case was everything that lives in the Gulf of Mexico, right? Or the Gulf of California. Because what were they planning to do? They were going to take that brine and put it right back into the ocean, to this small contained ocean. So I think that part of the problem is that we can get pretty myopic about who the stakeholders who are involved. And if we bring in that third stakeholder, it becomes really obvious, like, oh, this is a non-starter. Yeah, good. All right.
Any questions on the right-hand side of me, left-hand side of Tai? Maybe
Excellent.
A question from my side. So I was wondering about the trade-offs that you were talking about in the beginning, where you have treatment costs and then you have basically avoided damage costs to people, a village, drinking water, and then you have the environment, which is basically a non-marketed impact.
Right.
So what happens with the modeling approach if you have basically a standard, an environmental standard? The trade-offs then basically don't seem to exist. Is that correct? Or are you looking at risk premiums because you're talking about exceedances of maybe thresholds or standards that you have in place? Or are you then talking about maybe paying a risk premium for avoiding the exceedance of a problem?
I think any one of these could be true. And the sort of simple answer is that some of the solutions that are shown in that period of space, that's assuming that they're all plausible or they're all allowable solutions. And if you had a limit that said you cannot discharge or you cannot allow water to go by your property boundary that's above some certain limit, any treatment that doesn't match that, doesn't meet that would be considered non-operable or non-functional. So that would be taken out of that period of space. But otherwise, I think you're right, that we're looking at if things are really, it's in a sense, it's still evaluation, but it's trying to get away from putting a monetary value on it. It's saying, you know, we're looking at the trade-offs in whatever value system you want to use. What are these trade-offs that you want to use for deciding? And the other thing that I think it does help people to realize as stakeholders is often stakeholders will come into something thinking that their cost function looks like this, right? That there is a limit and anything that's above that limit is terrible and anything that's below that limit is fine, right? And through these kinds of conversations where you're talking about, like, really think about what you're asking here, because if you have this really sharp cost function, or this sharp distinction, then you're not allowing this company to come up with any sort of solutions that may work for you and they may be willing to do rather than just let you sue them. And so you're really limiting your power by having this strict function. Yeah.
Nancy.
Hey, we got one.
Thank you.
Did they all get together and say, you asked this one? Yeah.
So much pressure. Hi, I'm Nancy. I'm the Knowledge Mobilization Specialist at the Water Institute. So this talk was really interesting to me. I'm not a hydrogeologist and I'm not a modeler, but I do care about trying to find ways to incorporate stakeholder input and feedback into models. And so I think I heard or understood that you're talking about, you know, using input through the prior to be able to judge what your model's going to assess.
Right.
Can you think of other places during the model development where you might be thinking about how there might be opportunities to incorporate stakeholder feedback into the model?
Yeah, it's a good question. And so and maybe too far of an analogy, but I bike commute every day, right? And so as a bike commuter, you can tell me what the chances are that somebody's going to get hit by a car. But if I'm coming up to an intersection and somebody's driving and they're not slowing down yet, I'm going to react, right? And so my prior is, I don't care what the statistics tell me. My prior is, I don't want that car to hit me because they're looking at their phone, right? And that means that I'm going to collect different data and I'm going to behave differently and I'm going to need different data to change my mind, right? I need to see them slowing down. I need to see their eyes before I say, okay, I'm just going to go, right? So it's all about that, right? It's all about people who are making any kind of decision have all of this weight of their expectations coming in. And so it's really what this is all about is how do we make sure that we, who have the capability to do it, honor those concerns. And we can honor those concerns in considering trade-off solutions. I think the biggest one is this last one of really not getting comfortable with saying, I have a model that has an RMSE that's incredibly small, and look how great my RMSE is, and just stop there, right? Rather than saying, am I really doing my job for this person? I don't know if that answers your question. I'm happy to talk to you more about it. And thank you for asking on behalf of this side of the room. So, good.
We're waiting for the lunch, so please help me out here. Another question.
I said at the onset that I like to sort of set expectations or set examples for students. And one of them is use a controversial title. And that's a positive example. And the negative example is use 100 slides in 40 minutes. And then I actually went too fast, so that's okay.
I have another question.
All right.
Hi, Ty.
Hey.
Paul Martin here. Yeah, I just wanted to, if you could comment on the difference between using simplified versus more complex models to produce your posterior distribution. And how do you find that right balance? What are your considerations?
Yes, this is a great question. I intentionally did this in a very simple way, right? And so all of the models that we were comparing were really the same model with different parameter values. And so it was really easy to compare which one was better than the other. And when we get into model complexity, the real challenge is that essentially it's much easier to fit data with a much more complicated model. You have many more degrees of freedom, and so you can fit my signature if you want to, right? So you should hold those to a higher account. And there are some metrics to do that, but I think that where I've come down to on that is that we should always be required to defend any complication that we add to a model. So we should always start, in the sense, the simplest model that we think captures the physics. And if we want to add something extra, we need to defend why we're doing that. Now, part of this talk gives you some license to do that, right? You might say an equivalent porous medium model isn't really going to capture the behavior if there are faults in the system, right? So there might be a fault that goes directly from that plant to your well, and if you don't include it, then that's not really representing the system. That, in my mind, is a justifiable increase in complexity of the model. So I guess I just sort of wishy-washy fall back on the simplest models that you can come up with that are representing the physics in the model. It's a really good question, too, when we start thinking about this inclusion of machine learning models. Like, are those more complex models? Are they less complex models? I mean, in terms of number of parameters, they're millions of parameters. But in terms of processes, so I don't know. I don't know how we're going to deal with that when we start having these mixed models. And yeah, good question. Yeah.
Can you mix models within the same ensemble? Like, would you add a bioscreen model with different sets of parameters to a mod flow model?
I think you absolutely should. Yeah, absolutely. Yeah, no question. Yeah, and the difficulty comes in how you assess and how you assign likelihoods to these models, and how you penalize them. So any of these information content metrics penalize for complexity one way or another. Yeah, good. But I think, yeah, including multiple models.
One more question, maybe? You're on the
Yeah.
right-hand side? Where? Okay.
Thanks for the talk. Nice to hear you again. Heard you at the 2016 Darcy lecture. So I want to come back to the idea of different thresholds for convincing people based on the data. Can you say a bit more about that and how that, I didn't quite understand how that plays into your Pareto surfaces or the utility maps or whatever.
Yeah, it's a good point. So those Pareto surfaces are based on single predictions. So the Pareto surface formation would be after you've done your model weighting or you've done your assessment, say a Bayesian type assessment of the likely outcome. So in terms of the level that someone needs to be convinced, this again is going to vary with the stakeholder, right? And so you're essentially saying, the question that you're asking somebody is, what would I need to show you to change your mind, right? And if somebody says from the outset, there's nothing that your models could show me to change my mind, then stop talking to them, honestly. I mean, you're tilting at windmills. You're not really doing any good. So you can make that point to them, that say, I'm doing this analysis to help you decide whether or not you should change your mind. So work with me here, right? And those thresholds of belief or changing of opinion will differ. It's not always, if my posterior is 51%, then I'm okay, right? So yeah, these are good questions.
Does that impact the limit?
The limit, I would say, I see. Yeah, so that limit is sort of a different, simplified way of looking at it, where the limit you can think of as a utility function that's a step, right? So as you were asking. So if something's above the limit, it's bad, and if it's below the limit, it's good. So utility goes from 1 when it's below to 0 when it's above. So that's sort of a vehicle for thinking about how we can impose a utility function or define a utility function. But the full utility function would allow for some intermediate valuation. So it's a suggested limit, maybe something like that. Yeah.
Ty, do you have maybe examples of where stakeholders perhaps change their opinion or their perception based on the modeling exercise that you then did?
Yeah, I would say even in this mining case, starting out, people were well, I mean, in this case, it was a kind of a classic thing. So people were worried about flooding, right, in the town. And the mine had already done a regional model, and they showed this regional model, and they showed the distribution of flooding events. And they said, look, the water that we're putting out, there's so little water that we're putting out compared to a flood, it really doesn't make a difference, right? So then a stakeholder group got together, and they hired another consultant who came in and said, let's look at the frequency of things that are almost floods, right? Like a little bit more water than you'd like to have on the street. And then, of course, this makes a big difference. So now they're confronted with 2 different models, right? And one of them is saying, this is going to be disastrous. You're going to have 5 times as many floods as before. And the other one says it makes no difference. So in this case, it really was having a conversation about what do you mean by a flood and what's the risk here? And don't say I'm worried about a flood. Say I'm worried about not being able to drive down the street, or I'm worried about damage to buildings, or I'm worried about, and so that you can change their valuation in that sense by changing their definition. Yeah.
Right.
Good.
I think I should stop dragging this on and on and on. I believe that the lunch it takes 10 more minutes. I propose we give Ty a break. Let's give him a hand of applause once again for